Thanks for the invitation. I'm in charge of CBMM, the Center for Brains, Minds and Machines, which is an SF-funded center, 10 years, $50 million, mainly MIT and Harvard. And CBMM is becoming the core part of this Intelligence Quest initiative that MIT started a couple of months ago, institute-wide. And the core of this Intelligence Quest should be about the science and the engineering of intelligence. There is a lot of engineering that has been going on in the last 4 or 5 years because of companies like Google and Amazon and Facebook and so on. There's not actually as much science, meaning natural science, meaning neuroscience, meaning understanding intelligence, human intelligence. And so that's what our center is about and what the core of the Intelligence Initiative is. But I'll not speak about this at all. So I'll speak about really mathematics, which I regard as engineering. Mathematics is, science is where you get Nobel Prizes. So exactly, mathematics is not one of the areas where you get the Nobel Prize. Engineering is where you get Turing Prizes and money. And so mathematics is actually engineering, is studying human artifacts and not natural things. Of why deep networks work as well as they do. And there are many questions you can ask, of course. Let's consider deep neural networks with RLUs and gradient or stochastic gradient descent as a way to optimize the weights. And the question one can ask are, as I said, many, but at least there are 3 different classes of question. One is about approximation theory, one is about optimization, and one about machine learning or generalization. So the first one, again, you can formulate in various ways. I'm curious why and when are deep networks better than shallow networks? And first of all, this is something that I use throughout the various points. You can argue that you can approximate a deep network in terms of a very high degree, very high dimensional polynomial. You can argue that from the theory point of view, but to make things simple, we have done some empirical work in which we have replaced every RLU in a network and with a polynomial, in this case of 9 degree or so, and the network, which is now a polynomial, behaves, for all you can say empirically, as well as the network with RLUs. Okay? So I'll speak interchangeably about standard RLU networks or polynomial networks, meaning networks where the RLU has been replaced by a polynomial approximation. Okay, so the first question is about approximation, and this is back to different things that have been said already by several speakers, and it's well known since the 80s that networks with one hidden layer can approximate arbitrarily well any continuous function on a bounded domain. And this, in a sense, did, in the 80s and 90s, contribute to stop work or theoretical work on multi-layer networks, because it looked like you don't need multi-layer networks to approximate any particular class of function. You can do everything with shallow networks. Shallow networks being one hidden layer, for instance, kernel machines, which can be written in terms of one hidden layers networks. So, but then you realize that this is a recurring theme in approximation theory and optimization theory, is that when you want to represent a function of many variables, you are against this curse of dimensionality. The number of parameters that you need to approximate a function of d variables is in the order of 1 over epsilon, where the epsilon is the error you want to make in approximation in the sup norm to the d. And so suppose epsilon is 10%, so 1 over epsilon is 10, and suppose d is 8, you have 10 to the 8, but suppose d is, like 10,000 or something like this, like for some of the images in CIFAR, this would be like 1,000. You have 10 to the 1,000 as this number, rough order of magnitude, which is a large number. So both shallow and deep networks suffer from this, from the curse of dimensionality. And by the way, it's interesting to look at the history here. The standard way for people to try to counter the curse of dimensionality has been to assume smoothness properties of the function, the target functions. Because, in fact, if you look at it, I did not write it here, but the exponential dependence is d over s, where s is some measure of smoothness, like the number of derivatives of the function you want to approximate. And in fact, in the maybe 80s or 90s, there were at some point, I remember Terry Sejnowski said, this result of Andrew Barron shows that neural networks don't have the curse of dimensionality, but it was simply because Andrew Barron had a very nice result in which the class of function for which there was no curse of dimensionality was defined in a way that as the dimensionality increases, the smoothness increases. And so it was cancelling d over s, was remaining constant. Now, we are looking, looked at a different way, classes of function, not smoothness, but what we call compositionality. More precisely, it would be hierarchical local compositionality. So you have a function of many variables, say 8 variables in this case, which is a function of function of function, but each function is a function of a small number of variables. In this example, 2. Each one of these functions, g3, g21, g11, are a function of 2 variables. 2 is not important, you could have 3 or 4, but it should be a small bounded number of variables. Then, in this case, it's pretty easy to see that a deep network, but not a shallow one, can approximate functions, compositional functions of this type, without the curse of dimensionality. The number of parameters will depend linearly on the dimensionality. And there will be a factor that depends on the dimensionality of the local constituent function. So, the proof is pretty simple. It's in one slide. I will not go through it because I want to speak about 2 other things, but it's essentially checking that you can approximate a very local function with, for example, the example before, with an order of parameters which is in the order of epsilon to the 2, and the error does not propagate when you approximate. That's basically what happens. So again, if you have a generic function, you don't know anything about it, then shallow and deep network will be similar in terms of performance, and they will have the curse of dimensionality. But the function you want to approximate is compositional as a structure like this one, like this binary tree. The graph above is not a network, it's the graph of the function, in which you have essentially local computation at the various levels. Then a deep network will need many fewer parameters, exponentially fewer parameters than in the generic case. And by the way, there are connections here to the talk of Amnon, because the function that have the structure are the function that can be well approximated by tensor in the Tucker decomposition. So there is a clear connection. It's kind of, this type of approach gives foundations to what Amnon was saying. Some numerical experiment to confirm that, in fact, on CIFAR, to confirm that, in fact, if you have networks that are compositional, you can get much better and better accuracy. It's interesting in the theorem and also in the numerical experiment that this killing the exponential curse of dimensionality is not weight sharing, but locality of the functions. So weight sharing helps, but not in an exponential way. Helps in the sense of diminishing the number of parameters. But what kills the exponential is the locality of the constituent functions. So, for instance, a network that is local like this, even without weight sharing, will not suffer the exponential curse of dimensionality for the appropriate function. There is this interesting question, why are compositional functions interesting? Why they come up in problems with curve? And I don't know an answer to this. It's intuitive that, that when you are dealing with things like text or speech, where you have elements which, like sentences that are composition of words, which are themselves composition of letters, it's intuitive that you may have this structure in the function you want to learn, for instance, for classification or so. But for images, it's less clear. It's kind of intuitive again that you don't need to compute interaction between the pixel there and the pixel here. You can compute something here and something here, like objects, and then compose them for computing a scene. I was not able to find a real good argument about it. But essentially, the other thing, I cannot expect deep networks to work as well for every type of function, but only for a function that has this compositional structure, and in that case, the one you expect to work best are the convolutional ones. So dense networks are not, with some caveats, but are not really able to win even for compositional functions. So, as I said, locality is the important thing. Why compositional functions are important, at least in some of the problems. It's an open question. And let me go to the next question, and here is about optimization. Well, it's relatively easy to optimize, to find minima. And here I'm not providing any real theorem, but just some, some reasonably simple arguments. The first one is assume you're able to fit the data exactly, which, for instance, we can do in CIFAR. So it's not so difficult, probably not in ImageNet, but in CIFAR. So this means that your network for each image, xi, can exactly interpolate your y. Okay, this is in the framework of regression. Now I write P because I'm taking a polynomial network. I'm assuming this network, CIFAR, I've replaced all the RLU with a polynomial, a univariate polynomial. Then what I get for the network is a polynomial, high degree. And then I have, for CIFAR, I'll have 60,000 such equations for the different images in the training set. And the parameters are actually more than 60,000, typically 300,000. But even look, forgetting this, assuming that you have as many parameters as data point, Bézout theorem tells you an upper bound that seems to be reasonably within a factor of 2 or so, pretty good also in terms of being an effective bounds, an effective estimate of the number of solutions for the parameters of these polynomials. And it turns out that in the case of CIFAR, we probably have more solution, more zeros than atoms in the universe. So a lot of minima, global minima. This is because you have the degree of each polynomial to an exponent, which is the number of equations. Okay, so consider, these are for exact fitting of the data, 0 error. Consider the local minima conditions. There you have those equations, zeros of the gradient. Again, you have derivatives of a polynomial, which is a polynomial. I can again use Bézout theorem, and this time I have as many equations as unknowns in general. So there are a very large number of local minima, including the global minima. In general, they are not degenerate, unlike the global minima case. The global minima case, these ones, tend to be degenerate because you have fewer equations than parameters. Typically, you're using, say, 200,000 weights and 60,000 training points. So the conclusion here, you have many minima, and the global one, the 0 minima, are degenerate, and the local minima tend to be non-degenerate. Okay, so just a reminder of the Langevin equation in physics, which is basically the stochastic differential equation describing the motion of a particle in a potential well called V, and dB is the derivative of the Brownian motion, so white noise. And we know that the asymptotic solution of this thing is the Boltzmann distribution. This is a typo. And so I'm making here an analogy that empirically seems to work, is that in stochastic gradient descent, the fact that you are taking random samples from all the examples, you can write this as a pseudo noise. So when you look at the descent, it's like having the Langevin equation. This pseudo noise is not really a white noise, the derivative of the Brownian motion, but in practice it seems to behave in a very similar way. And so what you expect if you look at the Boltzmann distribution is that you will find most of the probability mass in large volumes of the potential of the loss function. And in fact, you can see here, if I have two minima, so this is using the Langevin equation, so gradient descent Langevin, and I have two minima, they are equally deep, but one has a linear dimension twice the other one, so it's a square hole. And if I start in one dimension, the asymptotic distribution is on the top left. I have more mass in the larger one, but not so much. I increase to 2 dimension, 3, 4, 5 dimension. 5 dimension, I don't see the smaller hole anymore. remember that in CIFAR we have around 200,000 dimensions. So there is a very strong probability concentration phenomenon here. And you can see this, this is comparing stochastic gradient descent Langevin, which is the normal stochastic gradient descent for a potential function like this. And more interestingly, you can see here that in 5 dimensions, this local minima, which is the same depth as this degenerate minima here, this minima has one direction of the Hessian, which is correspond to a 0 eigenvalue, so it's degenerate. So you see that as the dimensionality increases, stochastic gradient descent finds this one, but it does not see the smaller one at all. So that's the argument to say that, roughly, I cannot make any sharp statement, but in general you expect to find there are a lot of minima, and the global minima, which are zero error minima, can be found with very high probability by stochastic gradient descent, as opposed to the local minima. This does not say anything about generalization. It's just minima of the training error. Okay. The last question is, the reason why it's easy to optimize is, of course, because there are a lot of parameters, more parameters than data. So each of those, the general 0 are really a set of infinite number of points. But then how it comes that you don't overfit. I have more weights, parameters than data point. And here, the story seems to be the following. First of all, some empirical data. Here we did something, it's still with CIFAR, is a ResNet 5 layers. And we turned off every trick, so no data augmentation, no regularization. And you see, and this plots the result of, for a set of parameters, fixed set of parameters, what happens when you increase the number of training examples. So this is not iteration of gradient descent, we converge. And you see that, first of all, something expected, the more examples you have, the better your expected error is. You also see that as long as you have more parameters than data point, you can exactly fit the data. Training error is 0. But when the number of parameters is around the number of training examples, then you cannot fit the data anymore. And you can see also that as the number of examples increases, the architecture is fixed. As the number of examples increases, it looks like you have generalization, technically meaning that the training error converges to the test error for n going to infinity. I cannot really show converge, but it looks like these two things will go together. This would be generalization. It's not trivial because, for instance, k nearest neighbor, Olivier spoke about it, have generalization, but one nearest neighbor does not. And this is for the case of random labels. This was Xiwan Zhang was a student of mine, And here you see also this phenomenon of generalization. The test error is 90% because you have 10 classes and you have random labels, so it's chance. But as long as you have more parameters and data points, you can fit the data, zero error, like I found. But as you increase the number of training examples, then at some point you cannot fit the data, and it looks like the training error also will converge asymptotically to the test error. So again, generalization. Okay, so all of this is fine.
What's the yellow line?
Sorry?
What's the yellow line?
Oh, the yellow line is, so it's just the difference between the two. The generalization error, which is supposed to go to 0 for n going to infinity. Okay, we still have to answer this question. You know, classical overfitting is you have a function, you have some points, you want to predict the function, and there are many, many solutions unless you impose some constraints on the function class. Continuity is not enough, you need smoothness. And here, for CIFAR, we see again on a similar plot, but now here is the number of training data, and here I increase the number of weights in each of the 5 layers in the network. I see that as the number of parameters is above the number of data points, I can get 0 error like before. But the interesting thing is that as I increase the number of parameters, the generalization error does not get worse. This is absence of overfitting. This is classification error. And typically in overfitting, you would expect something like here going up, so there will be a minimum. Now, Olivier already mentioned one reason here. There is a very nice paper which came up in last October by Nate and Nati Srebro and co-workers, in which they show that for linear network, if you use cross entropy or the logistic loss or the exponential loss, then you converge to the minimum norm max marginal solution. This is well known with gradient descent. This is well known for the square loss, but for the square loss, the convergence to the minimum norm maximum margin solution is depending on the initial condition. You have to start with 0 weights or very small weights. The interesting part of this proof is that in the case of cross entropy, this is independent of initial condition. Now, in the case of linear network, does not make such a big difference, but and this is kind of what they show is essentially showing that the weights increase to infinity asymptotically, but what you are using for the classifier is the normalized set of weights, and that one converges. You can look at the paper. I think it's a very nice paper. And what we've been doing recently is to use tools from dynamical system theory to extend this result to deep nonlinear networks. So in dynamical systems, you have some results that tell you when a nonlinear dynamical system can be described in terms of a linear approximation around an equilibrium or some other points of the trajectory. And so what we were able to do is to prove that under some assumptions that are not too strong, the dynamical system that comes up from doing gradient descent on a nonlinear network using, in this case, the exponential loss, will behave near the asymptotic, so the way it will converge asymptotically will behave like a linearized system, and this linearized system is hyperbolic, and so it's as if it were regularized. We are also, I don't have the exact proof, but I think it should come out that if you regularize this, you converge to a finite W, in this case not increasing to infinity, and you have again the result which, for nonlinear systems, which can be described in terms of the regular result for linear networks. And the same probably happens, that's an interesting question, if instead of regularization, meaning an additional term in W square, the norm of W square added to the loss, if instead of this you have misclassification errors. So in that case it will work as a regularize, but don't take, I'm not 100% sure about this. So at this point, this last thing is a conjecture. Just to show you what you expect in this situation, and some experiment to show that this seems to be the case. This is kind of a square loss case in two variables, two ways. One direction is degenerate. By the way, when you have over-parameterized neural networks, we expect that the Hessian in general will be degenerate. So we'll expect a lot of direction like this for square error. And in the case of the exponential or cross-entropy loss, the situation is more like this. There will be many directions in which the surface is not flat but going to zero at infinity. Others, you may have convergence of weights to a finite values, and in this case W2. So if this picture is correct, you can do a small experiment. We make the following prediction. Suppose we do gradient descent, we are close to a minima, and then we are now perturbing the weights by some random perturbation. Then you would expect that if you run gradient descent again, the training error will go back to zero after the perturbation. But it will, if you repeat perturbation, you are moving your minimum, your particle, along the degenerate direction. So the other direction, it will go back to zero, but in the degenerate direction, things about the square laws, they are flat. You are perturbing, so it's like you are doing a diffusion process in that direction. So your norm will increase in general, perturbations after perturbations. And so we expect that after a lot of perturbation, training error goes back to zero, but the norm of the weights will increase and the generalization error will get worse. And we see exactly this kind of things. This is the cross entropy loss. This is the classification error. Those are the perturbations. These are weights of the network. So we see exactly this kind of predictions. Let's see, what else I can tell you there is, of course, implicit regularization, early stopping for the regression case, but let me show this. This one is the result. I think Olivier mentioned something like this. People usually show something like that. Again, this is not typical. These are number of parameters. This is number of training data, and typically you see this non-overfitting, this puzzling non-overfitting, but this is classification error. If you look at the cross-entropy loss, which is what you are minimizing, you see overfitting. And that fits exactly with the kind of description we have. You expect overfitting for the regression, the cross-entropy case in this case, but for classification, we know that it will converge anyway to the maximum margin solution, at least locally, and so you don't expect overfitting necessarily in that case. So in other words, a big part of this puzzle is that for nice data set, this is what Sibakov defined as low noise data set, then classification error is much more forgiving than the regression error in terms of overfitting. So that's kind of conclusion of what I said. And by the way, we cannot extend the result of Lebro to the case of square loss. And in fact, square loss behaves typically worse empirically. And the reason is that for square loss, there is dependency on the initial condition, and we cannot ensure that the initial conditions are zero of some of the component of the weights will remain zero before arriving to the local minimum. In general, they will not. For the cross entropy does not matter, because even if they are not zero, their cross entropy locally will convert to the maximum margin solution independently of the initial conditions. And so that's again an answer to some of the question. I think, like Olivier said, this to me says that there is no magic in what people, I scolded Chi Wan Zhang, my student, and Ben Recht about their paper, because looked like we needed a new theory for generalization. I don't think it's the case. It's just using some more or less standard results of things we know in the framework of the usual theory for explaining these apparent puzzles with deep networks. There are a number, of course, open questions here, just a couple. The first one is, why are many functions, when are they compositional? More rigorous results about optimization rather than these hand-waving arguments I described about stochastic gradient descent and the Langevin equation and so on. And then for the third one, we can say that there are many minima, global minima, and we can say that each one of them has a large margin, but different ones may have a better margin than others and generalize better. And I cannot tell you what makes one minimum. They're all zero error, but one minimum better than another one. I don't think it's the flatness. It's probably that, a combination of other things. Thank you.